Exactly. So what I thought is indeed, I'll tell you my story about this. It's maybe more interesting than just a boring talk about what it is. So about, what is it, a couple of weeks ago this happened. And yes, I was very excited because this is exactly what I wanted for a while. And to explain why, we should probably just start at the beginning. And there's two things in here. There's generic, and somewhere hidden, there's the word trait. So generic traits, how do they work? There's two ways of doing this. Well, there's the obvious one, which is a generic trait. So a trait that has a type argument. And yes, we're doing actual source code now. And then there's another option, which is associated types. And that happened in the name there, where instead of the generic type parameter being in the actual trait definition, it is hidden away in an associated type, like here in target. But the end result of both of them is the same, which is that it allows the trait to sort of be generic over the return value of methods. So here again, there is the trait, either the T or target or whatever, either there or either there. And what's the difference, and this is important, for the generic trait, a type can implement it multiple times. It can pick for the T here, it can pick different types and say, I do this, I do that. So a potential ASCII str type could say, I want to the sref as str and as U8, or as a U8 slice, because obviously a str is just a U8 slice. Whereas for an associated type, it can only implement the trait once. So there's only one deref, because otherwise the compiler would probably get all confused and turn into like multiple inheritance, C++. So you can only basically deref into one type. Now, if we throw these things together, sort of, but not really, we could have a potentially and completely pointless trait here, where there is the generic from the actual trait suddenly on the associated type. So we now basically sort of have a double sneaky ini of generics into the return value of a method. Why is this useful? Well, to do that, to find that out, we have to make the thing work. We need to talk about something that I call generic octet sequences. Imagine you're doing a network protocol parser. We talked about NTP, probably should have picked that. Instead, because I know it, let's talk a bit about DNS. In DNS packets, there is domain names. That's the www blah, blah, blah thing. And the way this is stored in DNS messages is a bit weird. It's broken up into labels. That's the bits between the dots if you write it out as in human form. And each label is preceded by the number of bytes in that label. So that's the 3, the 7, and the 3 there. And then the whole thing is ended with the empty label or a zero-length label, so just a 0 at the end. If you want to parse this out of a message, you have to do a little bit of work. So obviously, you want to do a function. So we have a message that holds all the data, the whole frame of the message. We stick it into evacuate, because why not? And we do a method parse dname, which just basically you say where your domain name starts. That's the index in the vector. And then it returns you a U8 slice with the actual message. Well, in a real implementation, obviously, you would wrap the U8 slice there into another type to get a bit smarter about it, but let's just stick with this. Also, there's probably a result for reality, because obviously people do things wrong. But that's nice, except U8 slices are a bit annoying if you want to keep the domain name around. Yeah, you could turn it into evacuate and do all of that, but there's a better way. If you are working in the Tokyo Hyper sort of ecosystem, then you probably heard about the bytes crate and the bytes type, which is sort of a U8 slice in an arc on steroids, kind of. But basically what it makes it very cheap to take bits out of a bytes object, copy them, and they're basically pointing to the same memory at the bottom. So you can make owned objects, which is nice because that bytes there doesn't have a lifetime. You can make owned objects without actually having to copy data and allocate and do all of these things. So, but the other one, the one with the UH slice, actually was kind of useful in cases where you don't need to keep it. So do we now need to implement two methods? Well, that's kind of stupid. So why not do this? Why not do traits? Because traits are fun and also make the compiler slow. So let's invent a trait called octets that represents a sequence of bytes. And we do our message now generic over that. And then we do the thing. And on octets, we'll just invent a associated type called range, which represents a range, like a bit part of that octets thing. Talk to me. This is how the trait could look. So we have a trait, we have this associated type range, which is returned by a simple method range. We're just using start and end here. In reality, you would probably use the range bounds thing. But let's just keep it simple. That looks great. So now we can basically, we have an octet sequence, and we can take a bit out of it and just keep it. So this is how we would probably implement it for an U8 slice. The range type here should probably be a reference to a U8 slice. Except, yeah, that doesn't work. So we need a lifetime here. And there's just absolutely no way to manufacture one, because the lifetime needs to be up there in the associated type. But we actually only get the lifetime that we need down here. So we need to get the lifetime up there, which we can't really do. There's no way to do that. We can, however, work around this and instead implement octets for a reference to a U8 slice. Because now we have the lifetime up there in the actual type definition, and we can then sneak it into the range type. Now it works. Does it also work for a VEC Q8? Well, no. Because now we have an undeclared lifetime, and again, where would we get that from? It would again live in the self pointer. But wait, we can do the exact same thing as we did before. We'll just do this on a reference to the VEC Q8. And then we have our tick A, and then everything is great. So basically what we're doing here is our octets trait isn't actually on the octet sequence itself, it's on a reference to the octet trait, to the octet sequence. So let's just rename it, say that it's now a reference to an octets range. We can clean it up a bit. We can just ditch the reference there, because of course references are copies, so that's all fine. That all works out. That's immutable references, obviously. And we can then go off and implement this also on like this. It looks exactly the same as we've seen the other one. Let's just try if this also works for the bytes thing, where we don't actually need the lifetime in here because we get an own time back. And indeed, this will work. The compiler doesn't complain about this at all, unless I made a mistake. And if we then use this, our lifetime, our trait bounds get a bit weird, because we now don't do bounds on the actual generic or on the actual generic type. We actually do trait bounds on a pointer or reference to that type. So you get these fun little higher kind of lifetimes. Looks a bit iffy, but it's fine. But also, we don't have that anymore, because that now lives on the reference as well. So we need to change this into that thing there, which starts to look even iffier. But it works. It's great. So that's what I was actually using. The lifetime bounds or the trait bounds get really weird if you have more complicated requirements. Like if you have two type parameters, like if you do a partial eq or something, then you suddenly have that twice, and then you have to. But we have a smart compiler. You just poke at it until it's not complaining anymore. Now, with GATs, or GATs, I still don't actually know what the proper pronunciation is, let's look at how we do it with that. So remember when we got this arrow way up? And remember the very first slide, or the third slide, I think, was it where I showed a gutsy kind of thing, which included this. The associated type now suddenly had a lifetime here. And that actually works. This is exactly what we need. We need the lifetime there instead of there. So let's just fix our trait. We'll stick the little tick A in there. And then what is important now is, obviously, you also need the tick A when you're using that range. So self range at the end there now needs to also contain that lifetime. And this is where the sort of degenerification comes in. It needs to come from somewhere within that method. So obviously, we have a tick A, which we take from self and transfer it to the range. Because we just do the self thing, we actually don't need the explicit lifetime arguments here. We can just use the underscore lifetime thing. That looks much better. Does it work? Yeah. Does it work for? Oh, it doesn't. So what happens is the compiler will complain with this in its usual very helpful and wordy way. It will tell you that there's a required bound. It even tells you what it needs to be. And it politely says that actually we just put that in because it needs to be there, but we don't really know if we really want this. So, unless you do, you just listen to the compiler and stick that in there. Well, it actually totally makes sense because, of course, the lifetime A can indeed not be longer than the type itself. Well, that would be weird. So we just do that, and then it all works. Does it work for bytes? Yes, which is interesting because our associated type, the one that we're actually putting into the implementation, it doesn't even have the lifetime. But it sort of does, because of course it has a static lifetime, and the static lifetime is longer than tick A, so that all works out. Which now means this is our trait bound, which is nicer. And as I said, if you have very complicated and long thingy things, then starting out with this is of course much nicer than if you have to start out with very complicated and gets ever more so complicated. At this point, our sponsor, which is this thing, which is the octet crate, which is exactly what that all is. So it was part of the domain crate, which is our DNS crate, which I wrote. And when we also started to do a BGP crate, which does all of these BGP parsing and things and whatnots, I figured, hey, they could use that too. So we turned this into the octet crate. It wanted to call it octets, but someone, about 3 days before I published it, stole the name. So it's now the octet crate after some very low-level bike shedding. So it started out with all these complicated things. Here's the new octets trait, which is exactly as well, it has also another trait bound there. But it's exactly as I showed it, and also has the range bound so that you can actually just say range ... and other weird things, rather than having to provide two numbers. That's already almost it, except that the announcement spoke of lifetime, type, and const generics. So you cannot only use lifetimes there, you can also stick types in there. Like this is the example from the announcement, which I think it's slightly constructed. I'm not sure. So I don't think there's really as sort of obvious examples for using types here as like lifetime is the thing that what you want it for. Probably come up with something to use there too. And then of course with const generics, that's all arrays somehow down the line somewhere, because that's what that's good for. And that's already it. Thank you. Any questions? I don't see anything.
Now you're stung.
Who put up these lights?
No good question. Thank you. So as far as I know, GATs still have some limitations. Can you tell us something about the limitations and if you've hit them already?
No.
I guess I was not informed that well then.
No, you're probably right, but I haven't, like, I only use it for the lifetime things, and for that it just worked great.
Yeah. So I was really hyped about GATs too. So I was trying to explain my friends what they do, and it's really difficult to explain in one sentence. Would you want to try?
Yes, so what they do, let's go back to where we did the thing. Even though I hate this, people's going back through their slides, but why not? Where are we? Where are we here? Is that the one? Well, the proper one. Let's do the proper one. What they allow you to do is to have trait methods inject types into the return type. I think that's the most practical value, right? So isn't there like a pointy thing here? Yeah. That's not it. It's a laser. Like this type argument here, right? It gets chosen by essentially, I guess we should probably go back. Sorry. Should go back here. This is more obvious, right? So the method here can choose what goes into that return type. And that wasn't possible earlier. Yeah. Oh, right, microphone.
Yeah, I think last time I had this problem. I was trying to implement an iterator in an efficient way with lifetime.
That's the usual case. I didn't want to use that one because everyone comes up with that one.
Yeah, it's like,
and also
for me, it's the case I remember the most.
For like ever. And you can ask Luke, he's back there somewhere. He tried to implement these lifetime bounds that I made up in the old version. And he tried to do that in the BGP crate, and it was very painful. So this is really great.
Yeah, so I'm not sure what you want me to say, but I never managed, so I also had to wait for 1.6.5, so this was stable. And now I'm actually refactoring into the new version of OXEC, and it's far better already.
Yeah.
So thanks for that.
Anyone else? No? Okay.